Hi, welcome to the 21st lecture of our graduate combinatorics course. Today we'll start where we left off in the previous lecture, namely talking about degree sequences. And in particular, we'll discuss this theorem of Havel and Hakimi, which gives a necessary and sufficient condition for a sequence of non-negative integers to be graphic, to be a degree sequence of a simple graph. So the theorem is stated on the screen, and let's say we're given a natural number n, and this non-increasing sequence of non-negative integers d1, d2, all the way up to dn. And the theorem states that there exists a simple graph gamma with vertex at v1, v2, all the way up to vn, such that the degree of vj equals dj for any j between 1 and n, if and only if there exists a simple graph gamma prime on n minus 1 vertices, whose degree sequence is d2 minus 1 all the way up to dt plus 1 minus 1, and then dt plus 2 all the way up to dn, where t equals d1. So the meaning of this theorem is that checking whether or not a sequence is a degree sequence of a simple graph on n vertices can be reduced to checking that a sequence of n minus 1 non-negative integers is a degree sequence of a simple graph on n minus 1 vertices. So it gives you a recursive procedure for verifying whether or not the degree sequence is a graphic sequence for a simple graph. So we'll see some examples after we prove the theorem. Last time, as you may recall, we proved this implication. So let's say assume, so I'll quickly go over that argument. Assume that there exists a simple graph. So simple graph means no loops and no multiple edges. Gamma prime, let's say with vertices v prime and a prime, such that v prime, let's just call it v2 all the way up to vn, and degree of v2 is d2 minus 1 all the way up to a degree of vt plus 1 is dt plus 1 minus 1, degree of vt plus 2, dt plus 2, and so on. Okay, so now this graph, as we did last time, you can draw the vertices here. So let's use two colors. So you can draw v2 all the way up to vt plus 1, and then you have vt plus 2 all the way up to vn, the vertices that have the same degrees as in as the one that we want. Now, so we have this graph, gamma prime, with this vertex set and with this degree sequence. And what we do is we just add a new vertex, let's call it v1, and we make this vertex v1 adjacent to this these vertices v2 all the way up to t plus 1. Now, what do we know? We know that t equals d1. So from v2 all the way up to vt plus 1, here we'll have exactly d1 vertices. So the degree of v1 will be d1. And now the degree of each of these vertices, v2 up to vt plus 1, will increase by 1. So it will become what we want, d2 all the way up to dt plus 1. And the degrees of these vertices, the back, it doesn't change. So these degrees stay dt plus 2 dn. And now, since gamma prime was a simple graph, and we added this a new vertex, and we added edges between these new vertex and previously existing vertices, we didn't create any loops, we didn't create any multiple edges. So this new graph will be simple graph, and we are done. Okay. Now, how does the other implication work? That's the more interesting one. So let's say, assume that there is a graph gamma with v equal v1, v2 all the way up to vn, degree of vj equals, so a simple graph, degree of vj is dj for any j between 1 and n. We want show that there exists a graph gamma prime with, again, a simple graph gamma prime with degree sequence d2 minus 1, dt plus 1 minus 1, dt plus 2, dn, where t equals is d1. Okay. Okay. So the light blue paragraph there, that's our hypothesis. So we have this graph, and let's look at it as follows. So let's look at the vertex v1, put it on one side, and then we have v2, we have all the way up to vt plus 1, vt plus 2, all the way up to vn. Okay, so this is our, this here is our graph gamma. And, you know, v1 could be adjacent to some of these vertices, to exactly t of them. So we have that the degree of v1 equals d1, which is t. Okay. Now, we get, the proof will work by cases. So case one is, in some sense, the easy one. So in the case one is we have the case that the vertex v1 is adjacent to v2 all the way up to vt plus 1. So it's adjacent to the vertices of the whose degrees are immediately below it. So in my picture, it will be like this. It'll be adjacent here all the way up to here. Okay. So in this case, what we are going to do is we're going to remove the vertex v1 from the graph. So deleting v1, and automatically the edges incident with it incident. v1 from gamma, we get a graph gamma prime, and here we can check fairly quickly. So in the in this graph gamma prime, this graph will be just on the vertex set, will have n minus 1 vertices. And what are the degrees going to be? Well, for here, these vertices at the end, the degrees don't change because nothing has changed there. So the degrees are still dt plus 2 all the way up to the n. And what about the other ones? Well, the degree of vertex v2 will drop by 1, so it will be d2 minus 1, and so on. The degree of dt plus 1 will drop, of vt plus 1 will drop by 1. So this graph will have exactly the degree sequence that we want here. And so we are done in this case. So we can say we get the graph gamma prime with the desired degree sequence. Okay, so this was the easy case when, you know, we ended up being lucky. We get this graph in which the vertex v1 is adjacent to all the vertices whose degrees are immediately below it. Okay. But of course, we can have a case 2. And let me draw the picture again here. So we have v1 here. We have v2, vt plus 1, vt plus 2, all the way up to vn. And this is the graph gamma. So in case 2, you can say that there is j, with j between 2 and t plus 1, such that v1 is not adjacent to vj. It's exactly the complement of the previous situation. Is so you have this vertex, some vertex vj here that I draw the non-edge as a dotted line. Okay. All right. So now how, we cannot do the same procedure of deleting the vertex V1 because now that may affect other vertices. So we don't know their degrees. So somehow in case 2, what we want to do is to change the graph, to modify the graph gamma to try to get it closer to case 1. Case 1 was the one in which everything was worked out the way we wanted. So how do we do that? Well, here's the argument. The degree of the vertex, so the degree of the vertex V1 is T, okay? And now the cardinality of this set, I'm saying something very obvious here, the cardinality of V2, Vt plus 1 is also T, but V1 is not adjacent, so I'll just, V1, I'll use this, not adjacent to Vj, okay? So there are T vertices from in this set here, V2 to Vt plus 1, and V1 is not adjacent to all of them, but V1 has to have T neighbors. So from here, it means that there exists K, let's say K between T plus 2 and N, such that V1 is adjacent to Vk. So there must be some vertex here, Vk, such that V1 is adjacent to. Because again, the graph is simple, so there are no loops and no multiple edges. So when we're counting the edges which contain V1 of them, V1 in them, we must get T such edges. And there is this edge V1, Vj is not there. Therefore, in order to get up to T, there must be some vertex Vk with K between T plus 2 and N such that this happens. V1 is adjacent to Vk. Okay. Now the argument continues in the following way. Because of our arrangement, it matters that we listed the vertices in the decreasing order like this, and these are the same thing as the vertices of dv1. This is dv2, and so on, dvn. So because k is greater than t plus 2 and j, j is between 2 and t plus 1, we must have that the degree of Vj is greater or equal than the degree of Vk. Okay. Now, Vk is adjacent to V1, but Vj is not adjacent to V1. Okay. So then, if we look at the neighbors, of Vj, which do not include V1, then that's the same thing as a set of neighbors of Vj. But if we look at the set of neighbors of Vk that do not include V1, that set is going to have cardinality degree of Vk minus 1. So from here, we get that the first thing is the obvious thing, that degree of Vj is strictly greater than the degree of Vk minus 1. And so combining these two other facts, we get that there exists some vertex VL, I don't know where L is, such that Vj is adjacent to VL, but Vk is not adjacent to VL. So there is some vertex, could be, I'll put it here, so I listed them there. Let's put it here, could be, well, maybe I'll do it here, can be, so let's say this is VL, such that Vj is adjacent here, but this vertex is not adjacent to Vk. Okay, maybe I'll draw it the other way around. It's a bit. So let's put it. That's some vertex Vj. This is, we have an edge here, but we don't have an edge here. Okay, so informally again, Vj has at least as many neighbors as Vk. Now Vk has one neighbor that Vj doesn't, so therefore Vj must have a neighbor that Vk doesn't. and that's this vertex, and not Vj. This is VL. Okay, and again, I drew VL there. I don't know where L is, if it's between 2 and t plus 1 or t plus 1 and n. It's anyway. Okay, so that's our picture. And now what we do is we change, let's call a graph gamma 1 is obtained from gamma by removing. So what we are going to do, we're going to switch two edges. So we're going to remove the edges V1, VK, I'll write it like this, and VJ, VL, and adding the edges V1, VJ, and VK, VL. Okay, so I'll draw the edges that appear now in purple. So I add this edge V1, VJ, and I add this edge VL, VK, and I delete this edge V1, VK, and I delete this edge VJ, VL. So by this procedure, this is a two switch. We switch two edges with two non-edges. What happens is that each of, if we look at these four vertices that are involved, V1, VJ, VK, and VL, each of them loses one edge, the one in blue, like dark blue or light blue, and it gains one edge, which is the purple one. So the degrees of the vertices of these four vertices stay the same, and the degrees of the remaining n-4 vertices stay the same because we don't do anything involving those vertices. So the degree sequence, the key thing is that the degree sequence of gamma 1 is the same as the degree sequence of gamma 1 is the same as the degree sequence of gamma, which is d1, d2, dn. Okay, but what's the difference between gamma 1 and gamma? Gamma 1 now is adjacent to more vertices from this first t plus 1, from these first t vertices, v2, v, all the way up to vt plus 1, than gamma was. So you see, we are in the case where in gamma, v1 is not adjacent to vj, but now we did this dance with these two edges, and which we switched, and we ended up with a graph gamma 1 in which has the same degree sequence, and v1 is adjacent to vj. And now we can repeat this procedure. If now we look at the graph gamma 1, if in the graph gamma 1, the vertex v1 is adjacent to all the vertices v2 up to vt plus 1, we are again in case 1, and when we are done. Otherwise, if there is a vertex in gamma 1 among those v2 up to vt plus 1, such that v1 is not adjacent to that vertex, we repeat this procedure. We do this argument in case 2 again, and we make vertex v1 adjacent with more vertices in that segment of t vertices. So because the graph is finite, and then in a finite number of steps, we are going to end up with a graph that has the same degree sequence as the one that we started with, and is a graph of case 1. So v1 is adjacent to every vertex in the set v2 up to vt plus 1, and then we delete v1 and we are done. Okay, so this is the argument of this proof. It's quite clever, and let's do some a simple example to see how this works on a kind in an algorithm kind of way. Example. So let's take a sequence 4, 3, 3, 2, 2, 1, 1. So this sequence is graphic. If and only if what we do is you look at the first, all the time the vertex of highest degree disappears. So you look at 4, and you look at 4 degrees that come after that, 4 numbers that come after that, and you subtract 1 from each of them. So now you will end up with a 2, a 2, a 1, a 1, and we have the 1 and 1 from before. Okay. Now note that when we do this procedure, sometimes the order of the resulting integers may be different than the one that we started with. So you have to always reorder these integers. In this case, in the first situation, that didn't happen. So now this one is equivalent to what? Well, again, we look at the first. This one is 2, and we are going to delete 1 from the next one. So we get a 1. You see, now we get a 0 here. We get a 1. We get a and the ones from before. And now, if you want to like here, you want to apply it again, you have to reorder them if you want. So you have two choices here. You can, if you want to apply the procedure again, you reorder the integers, so you end up with 1, 1, 1, 1, 0, and you can try to reorder, or to apply the algorithm again, or you can stop here. You can say, oh, do I know a graph which has this degree sequence? And you can work your way backwards. Okay, so these are the two possibilities. So let's say I stop here and I try to work my way backwards. So do we know a graph which has degree sequence 1, 0, 1, 1, 1? Well, so we can do, so the vertex of degree 0, it's called isolated vertex. So that's, it has no edges. And then the other ones, each of them have degree 1. So we can do one edge here, one edge here. We can call these vertices V1, V2, V3, V4, V5. So this sequence here, this one is graphic, because we have this, we can construct this graph. So this is implies that this sequence is graphic. And by the theorem that we just proved, implies that this sequence is also graphic. And how do we construct, so this sequence here, this graph here has degree sequence 1, 1, 1, 0. How do you construct one that has degree sequence 2, 2, and 4 1s? Well, we follow the procedure of kind of like the reverse of the first part of the Havel-Hakimi theorem. We add a new vertex, let's call it Vix6. So here the names of the vertices are different than kind of how we had them in the theorem, so don't worry about that. And now you have to, if you look here, we want V6 to be a vertex of degree 2, and we want to join him with join this vertex, join it with a vertex of degree 2 and a vertex of degree 1. So, which corresponds to a vertex of degree 1 and a vertex of degree 0 in this graph on 5 vertices. Now, for the vertex of degree 0, you have exactly one choice. For the other ones, you have many choices, but let's say we do this type of drawing. Okay, so now we have this graph. Let's draw it again here, and I'll write the degrees now, not the vertices. So here I have degree 2, degree 2, degree 1, degree 1, degree 1, degree 1, and this is exactly this degree sequence here. Okay, and now how do we end up back at this this degree sequence? Well, we add another vertex here, and we want this vertex to be degree 4, and we have it here that it has to be, we want it to be adjacent to these 4 vertices, which correspond to vertices of degree 2, 2, 1, 1 in this graph that we have here. And again, the solution is not going to be unique. You can have many choices here. So I need this vertex to be adjacent to the 2 vertices of degree 2. That could be here and here. And that changes their degree to 3 and to 3. And then I want the vertex to be adjacent of 2 vertices of degree 1. And there are many choices here. Let me do this one first. So that makes this vertex degree 4, this one degree 2, this one degree 2. And we have 4, 3, 3, 2, 2, 1, 1. But another solution would be like this. So this vertex here, join them here. But you could also join them actually this way, and you have the same degree sequence. You have 2, 3, 3, 2, 4, 1, 1. This graph is not connected. And there's another choice that I leave it to you to figure out. So I leave it to you as an exercise to try to figure out the last step, how many non-isomorphic graphs you find with this degree sequence, or with this degree sequence. The one here, this is just, I think there's only one graph with that degree sequence. So figure out the other two. Okay. All right. Now, so let's move on to something related to the first problem, the Euler's Königsberg bridges. So we had this problem with we argue that you cannot go through every edge exactly once and return to where you started, because the degree, in order for that to happen, the degree would have to be even at each vertex, but that was not the case for this graph. So what we want to prove now, we actually want to prove that this condition with the degree is actually both necessary and sufficient. But to do that, I need some definitions. So let's do some definitions. So we'll have a general situation of a graph gamma with vertex set V and edge set E. It could have loops, or it could have multiple edges. Now I will write here some notions. So first, we want to define what is a walk. So a walk is a sequence x0, e1, x1, all the way to up xk minus 1, ek, xk, where x0, x1, xk are vertices, e1, ek are edges, and ej is incident to both to xj minus 1 and xj for any j between 1 and k. So let me, I'll draw another graph here, because this would be a bit better for our example. So let me draw this. Okay. I want a graph that has a loop as well. Let's put a loop here. So this one is V1, V2, V3, V4, and V5. And then let's call the edges. I'll give them F1, F2, F3, F4, F5, F6, F7, F8, and the loop is F9. So here, a walk is essentially you start at the vertex, and you continue on. You use an edge which contains that vertex, and you end up to another vertex, and you can repeat this procedure. So you are moving, but you're moving on edges. You cannot just jump. For example, I cannot just jump from V2 to V5 because there's no edge to connect them. So in our situation, if I look at something like V3, F4, V4, so that's a valid walk. It gets me from V3 to V4 using the edge V4. I can go back on edge F4 if I want. I can use it again, going back to go to V3. I can use F7 to go to V5. I can use F9 to go to stay at V5. And then I can use F8 to go to V4 and so on. So this is a walk that goes from V3 to V4. I'm walking on edges. And in this situation, the length of the walk is k. So the length of this walk is the number of edges. K is the number of edges it uses. Okay. All right. So when you have a walk, think about it as, you're walking through a city or something. You can go back and forth for various points of interest. You can go, you don't have to go through different edges or vertices all the time. So you can repeat things. Now, a special type of walk is called a trail. And a trail is a walk with no repeated edges. Okay. So in our example, the example in light green, we repeat the edge F4. So that's a walk, but not a trail. Okay. So again, trail, think about hiking. Maybe you don't want to go back and forth to various paths, but you may end up in the same junctions multiple times. So for example, if I do V1, F2, V3, F4, V4, now I use a different edge. I use F5, I go back to V3, and then I go to F7 to V5. This is a trail, because in the list of edges, I don't use an edge twice, okay? And so one more thing before we go, a closed walk, I should mention this, is a walk where the starting point is the same as the last point. So x0 equals xk. So the walk above is not closed because V3 is not V4. And the trail that we describe is also not closed. And then a circuit is a closed trail. So again, it's a trail where, so you don't repeat edges, trail with x0, where the starting point is the same as the end point. So it's kind of like starting at the landmass and walking through all the bridges and coming back where you started. That's why we need this definition of closed. Now, one more definition is path, and a path is a walk with no repeated vertices. So here, in the first example we gave, we repeated edge, so we repeated also vertices. So that's not that's a walk. It's not a trail. We have a trail here, but we repeat V3 in two places, so that's a trail and is not a path. Okay. So if you want to do, so let me erase here. If you want to do something easy to remember is that, walk is the set of walks is the set of less restrictive things, and then you have trails, and then inside them you have paths. Okay, something like that. Okay. Now, just a few more definitions. The graph gamma is called connected if for any x not y in the vertex set, there exists a path between x and y. Also, sometimes we call it xy path that starts at x and ends up at y. And also here, like this walk that we describe here, this walk, we can call it x0, xk walk, just to specify the starting point, x0, and the last vertex, which is xk. Okay. So connected means that between any two vertices there is a path. Okay. And I think we have all the definitions that we need. Well, maybe not. One more. What is a cycle in the graph? A cycle is you have a walk of this, so x0, e1, xk minus 1, ek, xk. You have a walk where x1, x0 up to xk minus 1 are distinct, and x0 equals xk. Okay. So in our situation, in our example here, there's obvious cycle v1, f2, v3, f3, v2, f1, v1. That's a cycle. But there's also a cycle of the form v3, f4, v4, f5, v3. That's also a cycle. The first one has a cycle of, you use 3 edges, so it's a cycle of length 3. The second one is a cycle of length 2. You have these multiple edges. And you can also have v5, f9, v5. It's also a cycle. It's a cycle of length 1. That's a loop. Okay. All right. So what we are interested in, well, in our problem involving Königsberg bridges, you want to start at the vertex of the graph. You want to go to every edge exactly once, and you come back to where you started. So that going to every edge exactly once, that's so going to, no, we do not repeat edges, so that's a trail, and we, the ending point is the same as the starting point, so that's a closed trail. So in the Königsberg bridges, we're looking for a closed trail that goes through every edge exactly once. So that also has a name, and it's called a Eulerian circuit. So Eulerian circuit is a closed trail that contains each edge exactly once. Contains each edge, let me see, each edge of the graph. Okay. Because it's a trail, trail means that you no repeated edges. So each edge is contained at once, and so it contains each edge exactly once. Okay. So that's what the Eulerian circuit is. And again, in honor of Euler, the graph gamma is called Eulerian if it has an Eulerian circuit. Okay. Now, in Euler's paper, in 1736, he observed that if the graph contains an Eulerian circuit, he didn't call it this, and he didn't use the term of graphs, but you can rephrase it using this language. So in that situation, every vertex must have an even degree, because you have to go in the, when you go on this trail, you have to go in a vertex on some edge, and you have to exit that vertex on a different edge. So every time you go through a vertex, you have to use 2 edges. And for the starting and the ending point of the circuit, also the degree has to be even, because the edge on which you start can be paired up with the edge on which you use at the last step of the circuit. So now Euler didn't prove that this condition was sufficient. This was proved by Hierholzer later in the 1800s, and it appeared in an article after Hierholzer's death in 1873. So before we state the theorem, I need one more thing. So I need the notion of an isolated vertex. So a graph is isolated, it's a vertex of degree 0. So it has no edges incident with it. And now one simple observation is that if we have a graph gamma that is Eulerian, so there is one of these closed trails that contains every edge exactly once and so on, then having isolated vertices, it doesn't really affect this property. So if gamma is Eulerian, then gamma union any isolated vertices is also Eulerian. So we might as well, if you have any isolated vertices, you can just remove them and look at the graph that is left, and so check if that graph is Eulerian or not. So with that in mind, let's state this theorem. So Euler-Hierholzer. So at gamma, I will restrict myself to a connected graph, be a connected graph. So the graph gamma is Eulerian if and only if the degree of any of each vertex of gamma is even. So that's the theorem stating that the necessary condition for the existence of this Eulerian circuit is also sufficient. So let's prove it. So prove the direct implication: if gamma is Eulerian, then each vertex has even degree. We've done it before, so we discussed it earlier. So let's do the harder implication, which is let gamma be a connected graph. I won't write it again. With all the vertices even, then we want to prove that there is a closed trail that contains every edge of the graph exactly once. So for this implication, we will use strong induction on the number of edges. And we'll also use the following lemma, and this is quite useful. So it says that let gamma be a graph, you can take connected, be a connected graph with minimum degree, which I denote by delta of gamma, greater or equal to 2. So minimum degree, by definition, this is the minimum of d of x over all x in the vertex set of gamma. So if the minimum degree is at least 2, then what I want to prove is that the graph gamma contains a cycle. Now here, I will put that all the graphs we talk about in this class are finite, but I'll add this part finite here because it's important. So let's prove first the lemma. So what I do is the following: use finiteness. So let P, let's say x0, e1, x1, all the way up to xk minus 1, ek, xk, be a path of gamma with maximum length. I mean, all the paths are finite in the graph. So among all these paths, if you look at their lengths, the lengths are natural numbers or non-negative integer. You can say a path with a single vertex has length 0, but one of them has the largest length. There could be several, but pick one. Now we look at this at the vertex at the end for this path. So we have that the degree of xk is greater or equal to 2. Xk is adjacent to xk minus 1. So there must be some other vertex z such that z is not xk. Well, it could be, I mean, it may be, but there exists z such that, there is another edge which contains, so this is the edge ek. There exists another edge f such that xk belongs to f. Now, this edge cannot go outside towards a vertex z, which is not in the list of the previous vertices, because in that case, we would create a path that is longer than the path that of the largest length. So this situation cannot happen. So this xk has to have this path has to connect xk with one of the previous vertices xj. I mean, it could even be, this vertex xk minus 1 if you want, so on. And in this situation, so there is this f with this property, and f involves, so what we have here is that xk, f, xj, these are the two the vertices that are incident with f. And then if we look at this this part, start at xj, go the same way as we did in the path, all the way up to xk, and then come back to xj. This is our cycle. We have found the cycle. Okay. So every time you have degree at least 2, a cycle appears. Okay. And now, how does the proof of Euler-Hierholzer theorem goes? So we said we use strong induction on the number of edges. So if we have number of edges is 0, then the graph is isolated. So that's kind of not possible. Let's say if the number of edges is 1, then what could happen? Then we have this type of graph, and this is Eulerian. So you have one loop. Okay. So let's assume that, so these are the base cases. Base case. So for the induction step, assume the cardinality of E is M, which is something like greater or equal to 2, and assume the statement is true for all graphs, connected graphs with at most M minus 1 edges. Okay. Now, in our graph, because gamma is connected, so that implies that the degree of each vertex x is greater or equal to 1 for every x in V. But the degree is gamma. Each vertex of dx is even. Each vertex of gamma is even. So that implies that the degree of x must be greater or equal to 2 for any x in V. And by the previous lemma, using lemma, gamma contains a cycle. So what we have, let me draw it here. We're going to have a cycle here in this graph, see? And there could be things that kind of hang off it like this, or something like that, and so on, okay? You can have a loop, and so on. Okay, I mean, So now what we do is we look at gamma and we denote gamma prime, gamma minus the edges of C. So what happens in gamma prime, the degrees of gamma prime are even, because each vertex, if you have a vertex on the cycle, like this vertex here, it used to have degree 4, but now it loses 2 edges from the cycle, but it stays even. Or you could have vertices like this vertex here on the top is not on the cycle, so it doesn't lose any edge, so its degree stays the same. It's also even. Now, when you delete these edges, the graph gamma prime may not still be connected. So gamma prime may be disconnected. And you can have this picture, you see like these light blue components. Those are the components of gamma prime. So now each of these components of gamma prime, if it has at least one edge, it's going to be a connected graph in which the induction hypothesis is true. So each of these light blue graphs is going to contain an Eulerian circuit. So now, how do we get an Eulerian circuit for the big graph? Well, we start with the vertex of C. Let's say we start at this vertex here at the bottom, and we ask: is this vertex contained in a component of gamma prime? No. Well, it itself is a component of gamma prime. So in that case, we don't have to traverse any light blue graph. So we can continue. We start at this vertex and we go on the edges of the cycle C. We go here, the same situation at this vertex, and then we end up at this vertex. Now at this vertex, we have these light blue edges, this light blue component of gamma prime, and we know from the induction hypothesis that this gamma prime is actually an Eulerian graph. So because of that, we go here and we traverse each edge exactly once, and we return to where we started, okay? And when we come back to the vertex, the dark blue vertex, we continue on the cycle, and then we see if there's a component of gamma prime there, and then we use these light blue edges again, and we come back, and then we make a new step on the cycle. We use a light blue edge, walk on the cycle, use the light blue edges, and then walk on the cycle, and we come back to where we started. And this is, we've used every edge exactly once, because the edges of the graph are either in the cycle or outside the cycle. And we return to where we started. And that's the proof that the graph is Eulerian if all the degrees are even. And it gives you an algorithm. It's a recursive algorithm to find this Eulerian circuit.